We are recording. Thanks, David.
Ian.
See you. Okay, so come on. Yes, green. Wait, come on. Okay, so like I say, this is where you guys and you people on Zoom, the people on Zoom, firstly, can you guys on Zoom hear me? Gonna go with yes. Gonna hope that's the case. If not, I'll have to do the headphone thing, but that's okay. We may actually just wait a couple of minutes just until I don't know if there were, I can't tell from here whether there are people trying to get in here or not. Yeah, so I'm going to wait a couple of minutes to sort of start. And really, I'm just going to work through and talk about what could happen, find through some of the things that you might need to know. That's where you ask me questions, everybody has. Yeah. All right, because there's no point doing the slides if I don't get some audience interaction around. And I didn't I'm not very good. Oh, hang on, maybe. The trick with juggling something is you need something not too light. Yeah. So no, it's too. We can do this. Oh. There we go. See, you can juggle. Yeah. Yeah, no, it's big chunky chalk. It'll be fine. So you guys on the Zoom? Ah, there we go. There's the chat. That's what I'm looking for. Thank you, Aiden. Nice work. If you guys on the Zoom have questions, flick me a comment. And I might get David to just cut this preamble bit out so that when we'll do a proper introduction when we get time. I've been avoiding this type of long time. Oh. Yeah. Yes. Yeah, no, the waiting in front of class is really weird. Yeah. But they're only giving you the one example of that. Either way. Yeah, and then you multiply also. And then you put all of our like common cases of you think really. So I was in the like so sometimes what happens like all right, so we can do this. We can think about this for a second. So yeah,
That's very cool. Okay, okay. No, almost there. Okay, not bad. It was the one where it was like, the traces, these.
Okay, we could do workshop questions.
Yeah. Yes. I don't know the reason to be for that part, or because there's some lot that even if there were and it was even like, and there's even if there was one I found that not easy to. That could still have two I think that's not. Yeah, that's yeah, I was like, and there aren't really really practice, so I just and then I just like, yeah, that one's good, okay. Yeah. This one, yes, yeah, that was exactly not one of the books. This one, 22 points. Makes sense, right? Yeah, this one.
Okay. So today, I need to sit in front of this thing so it records properly. Today, my name's Nicholas. I'm from the Maths Learning Centre. Going to run a few through a few things from Maths 1B to give you a bit of a answer a few questions for the those people about to sit the exam. So we should reiterate, it is your responsibility to find out the time and place of your exam. Do never rely on me for anything. All right, I can do maths. Being able to turn up on time is a different skill altogether, and so being able to read what's in an email, separate skill. All right, so it's your responsibility to turn up to the exam on time, and so I'm not going to make any comments about when or where the exam is because I don't know. You should have been told. What I'm going to do, so there's a couple of people were suggesting looking at things like L'Hopital's rule. So what we might actually do is go back a little bit and talk about what we know, all right? Because what we're going to do with L'Hopital's rule is a reasonably simple idea, right? It's clever. It's actually kind of really clever, but what we're going to do is we're going to explore the limit laws that we theoretically learned in Maths 1A. All right. So when I've talked to people about L'Hopital's rule this last few weeks, it hasn't been about L'Hopital's rule per se. It's about two things: understanding the limit laws that we learned in Maths 1A, and knowing a couple of tricks. All right, couple of tricks, nothing up my sleeve. Hey presto. Okay, so that's actually the thing we're gonna we want to do. All right, so like what was that thing? There was a horrible thing which was like limit. I don't know. X goes to 1 of like x minus 1 to the x minus 1, something like that. I need to do this. Give me a second. Gonna stop to. This will make a lot more sense. Sweet. All right. Under the heading of things I don't necessarily do well, remembering to put the screen on the put the thing I'm doing on the screen could be one of those. Okay, so now I'm looking at this and going, I've deliberately chosen this so that this goes to 0 and this goes to 0, and I'm like, I have no idea. All right. So there's a whole lot of limit law things that we learn, right? And there's like limit x goes to a of f of x plus b of x, sure, that'll work. Limit x goes to a of f of x plus limit x goes to a of b of x. Right. There's a lot of there's several of them. There's one for constant multiple. There's one for the multiplication and addition. So there's like a limit of f of x times g of x going to be okay. I'm not going to try and write them all out. Those are the fairly straightforward ones, right? What we do want though is there's one that sort of says, what is it? So it's like a composition of limit. Now, there's a lot of, caveats around when you can apply this. Chiefly, that is that f of x is continuous. All right. And that the limit g exists. But we can actually go, this is f of limit x goes to a of g of x. Okay. Off the top of my head, there's another slight variation on this, which I'm reluctant to put down because I'm not sure I'm going to get it right. So I'm going to go, there's a slight variation on this. All right. But what that means is when we come to the question that we're talking about up here, I can do tricks to it. All right. This kind of says my limit going this way. This says I can sort of take the limit inside the composition of functions. Going this way, it says I can take it outside. All right. And so if we were to do a thing where we said this thing like limit x goes to 1, x minus 1 on, I may have done something that may not have a limit. All right. When you make stuff up on the spot, you potentially get it wrong. I'm going to say that's equal to some value. But then this thing says I can actually sort of go, well, I could apply a function to the outside. All right. So if I do ln of my limit, x goes to 1, x minus 1, x minus 1 is equal to ln of m. Now, but now I can apply my rule, which says I can put that limit on the inside. I should do, I want that way. That way. All right. And so I can go, this is like limit x goes to 1 of ln of x minus 1, x minus 1. Sweet. Okay, let's talk about what this bit is. Well, we're going to say it's equal to some ln of the limit. So the reason I've specified that is that it tells me I have to undo it to get what my limit actually is. All right, we kind of know about this one. So we're going to go, this is equal to limit x goes to 1 of x minus 1 times by ln of x minus 1. Now, this is a wonderful thing where, so for us to apply L'Hopital's rule, we have to have one of these indeterminate forms, all right? And it's important when you're answering a question in the exam that you state it satisfies an indeterminate form, all right? So we can go, all right, so x minus 1 goes to 0 and ln, ln of x minus 1 goes to minus infinity. Therefore, we have an indeterminate form. We could then try and rewrite this so that we've got something that's going to be easy to do. Easy to do. So normally we try and do this thing where we have like a 0 on 0 sort of form. And so we've got a 0, so we can do 1 on this to get the 0 here. So we can say this is equal to limit x goes to 1 of x minus 1 on 1 on ln of x minus 1. That may not have been the world's greatest plan. But anyway, we're going to work with it now. All right, work with it. So L'Hopital's rule tells me that this is going to be like limit x goes to 1 of, so derivative of the top line, just 1. Derivative of the bottom line, d by dx of 1 on ln of x minus 1. This is where I'm going. Did I do the right thing? I should have gone the other way. All right. Let's go one step. This is like minus 1 times ln of x minus 1 to the minus 2 times by derivative of ln of x, which is going to be 1 on x minus 1. And you kind of go, okay, that did not make my life easier. So there is nothing wrong with going, Cypress Hill, you're all stuffed up. All right. Favorite phrase. When all said and done, we go, hey, this wasn't a thing. But this is equivalent to saying limit x goes to 1 of ln of x minus 1 on 1 on x minus 1. Let's hope this works out better. And so I'm going to go limit x goes to 1. And then this bit is going to get me 1 on x minus 1. And this is going to get me minus 1 on x minus 1 squared. And I'm going to go boop. Sweet. And so it is equal to limit x goes to 1 on x minus 1 times by the reciprocal. Whoops, someone popped out. X minus 1 squared on 1. And so one of these cancels with one of these. And so I'm going to have 1 times x minus 1 times x minus 1 on 1. Technically, you actually have to say limit. Until we've actually evaluated at that point, all right, we're still saying limit. So we need to go limit x goes to whatever as you go through, all right? So if it's missing that bit, technically it's wrong. And so the marker may choose to be mean and go, I'm going to take a mark off because you didn't write the right thing. You know, most of them where it's clear you won't, they won't, but you should. X goes 1, that's going to be equal to 0. Equal to 0. All right, so therefore my ln of my limit is equal to 0. And so therefore my m is equal to 1. Whoops. All right. So I can do that trick. That trick. All right. So where we applied this idea, this is known as limit law 4. Not sure how it became limit law 4, whether it's just the Adelaide University of the lecture notes, like Adelaide University lecture notes. I'm pretty sure it's been limit law 4 since I was an undergrad. Yeah, that's why I'm going. Maybe it's in someone's text and I don't know. So where we took a function of that thing, and by having that composition of functions thing, the limit law that applies to the composition of functions, we're able to take sort of the ln inside the limit. All right. And then we can work through what's going to happen from there. So we can come up with an answer. This other bit, so I don't mind that I did this wrong, all right? Because I want you to know that sometimes you try something and it doesn't work, all right? And you should recognize it doesn't work and go, all right, I'm going to abandon this plan and try something else, right? I did an exam where I wrote, I had 10 attempts at this question. And I was like, got a little bit. I'm like, no, that's wrong. No, that's wrong. And then the worst part is I worked out what was right while I was walking to my car after the exam. I was like really, really annoyed. But anyway, my point is, you keep trying, all right? Because sometimes a skill is recognizing when you don't have the right answer, all right? Or when the approach you are taking is not going to work, all right? So being prepared to abandon an approach as you get along is an acceptable thing to do, okay? So, all right, cool. Are we happy with that? All right, so composition of functions, the limit can come inside or go outside of that composition of functions, all right? Just be careful. When we're doing L'Hopital's rule, justify why we have that indeterminate form, and then you say you can apply a L'Hopital's rule. So really, here I should say something like a couple of words to sort of make it a complete statement, actually is not actually a bad thing. So because this is the bit where we're saying, I've done this, I've observed these things, and so then I'm allowed to apply L'Hopital's rule. All right. That's I've actually, like, when you're trying to sort of, you're arguing with your mum, you're like, I don't need to do that because here I've done this. This thing is the thing that needed to be done, and therefore I've done what is required. All right. Mathematics is the same thing. I needed to show you these are going to go to, this is an indeterminate form. This is me showing you it's an indeterminate form. Therefore, all right. Okay. These things all are like, it's that process. What I have to do, this is me doing it. This is the conclusion I get from it. All right. Okay, cool. What we might do is I might go back to, where's that one? No, that one. Right one. Oh, that one. So I do not love the amount of white space between questions in the exam. So that was Gram-Schmidt prediction. Oh, okay. All right, sure. Sure, same thing. Oh, yep. Okay. That's an interesting function. I like that function. I'm gonna talk about that for a second. So with sort of thing partial derivatives and gradients, all right. So if I have my f of xy is equal to x arc tan, whoops, I'm gonna write this out and then I'm gonna switch. Okay. The question actually asks you to calculate, so I wanted to find f of xy. Right. Technically, I'm going to write that second derivative of f with respect to x and then with respect to y. F, x, y. We should know that that's equal to f of y, x. The order in which I do those two shouldn't matter. All right. If it's the right class of function, but I think just continuous. Okay. If I was to do this, right, what I would be doing is I'd be going, all right, I'm going to work out f of x first. All right. Whenever I do a partial derivative, I've got to be careful not to do that because it's fx and xy is what it really is. What I do is I say to myself, I'm differentiating with respect to x, holding all other variables constant. All right. And so that's what tells me that this bit has actually got to be a constant. And so this one is just going to be arctan of y. If I was to do it the other way, f of y is equal to, so again, x is going to be held constant. So I'm differentiating with respect to y. And the derivative of arctan of y is 1 plus y squared. Okay. So I can sort of go either way with this one. So I can differentiate with respect to x, with respect to y, with respect to x, with respect to y. So if I differentiate this with respect to x, I'm going to get 0 because there is no x's in there. Y is being held constant. It's like differentiating with 3 with respect to x. It's going to be 0. If I differentiate with respect to y, I'm going to get 1 on 1 plus y squared. If I differentiate this with respect to x, you can actually see that I'm going to get the same thing. All right, I'm going to get the same answer, all right, because my x is just x times y, this number, which is a constant. I'm just left with that constant. Let's call this number 7. 7x, derivative of 7x is just my 7. If I differentiate this with respect to y, suddenly gets very messy. All right, so I'm going to go minus 2y. I need an x in there. 1 plus y squared. All right, there was some chain rule thing happening. There's a few faces that are like, really? Okay, I didn't want to focus too much on that. Bear in mind, you can rewrite these things, right? What I did to make that easy for me to do is I've said this is x times 1 plus y squared to the minus 1. So I'm going to apply this, we're treating as a constant. So that's why I kind of put it in as an afterthought. That's why the confused look. Beautiful. Yeah. Like I say, tell me about these things. So minus 1 comes up the top. This thing to the power minus 2 times by the derivative of the inner function. That's where my 2y came from. So there is actually a thing I would do when I'm particularly with multivariable functions. I have a habit of trying to write my variables in alphabetical order. All right. If I'm rewriting this thing here, I will, because they're multiplied together, it doesn't matter which way around I put them. So I put them in alphabetical order. All right. Because so all the numbers go to the front. So I multiply them together to get a single value. I put them, it allows me to more easily recognize when I have the same thing. All right. And that's actually one of the things we want to do. We want to recognize when we have a common factor. And so putting all the variables in the same way allows us to do that. So if we were to talk about the grad vector for this particular thing, so grad of f, which would just be my partial derivatives, fx and fy. All right, that's going to be, well, arctan of y and x on 1 plus y squared. All right. Now, this is slightly different from some of the things you've been doing where you've been talking about doing a tangent plane, okay? And that is, for me to have a tangent plane, I need to have defined a surface, all right? And there is a couple of ways I can define a surface, okay? So I could define a surface. So I could say z is equal to f of x, y, all right? And so that's allowing me to go, my z value is dependent on this. So any xy point, get a height. I can interpret it as a height. And that defines a surface. The other way I could do this is I could have a function of x, y, and z. And so what this is doing is every point in my three-dimensional space, I assign a value. So the classic one they like to talk about is temperature. All right. But then my surface is kind of harder to see. All right. My surface is actually where this thing is equal to some constant. All right. So this is where, when I'm talking about my normal vector for my tangent plane, in this case, I'm going to rewrite this as f of x, y minus z is equal to 0. And so my grad for that, the grad of this is going to be equal to sort of fx, fy, and minus 1. Okay? Because I need to have the partial, so partial with respect to x, partial with respect to y, minus 1 is the partial with respect to z. All right. Remember, the grad vector is a direction vector. And in this case, its direction means something. So I want to set it up in a very specific way. Okay? Because rate of maximum increase is the direction of the grad vector. So in this case, my grad of my g, and it is grad of g in this case, is going to be equal to, and then partials with respect to x, with respect to y, and in this case, partial with respect to z. All right. There is mystical magical things about why this is the normal vector. All right. At this point in time, my answer is just accept that it's the normal vector. All right. If you're actually talking to David is kind of fun because he will tell you about the history of this and it's kind of fascinating. I don't remember it. I'm not going to try and tell that story. But we're going to accept that these are the gradient vectors. All right. Now, so once we've got our gradient vectors, we're going to want to find the normal plane. The tangent plane. All right. I think, did we have a, I'm going to do this for a second. What was the thing? Trying to remember what the thing was. No, I'm going to just, nobody's happy about that. All right, we'll talk about that in a second. No. Oh, we'll do that. Do that. I'll come back to that. Sweet. Okay. I'm going to see if I can remember one of the. Let's think about that, what that's going to do for a second. That's going to be a bit boring. All right. So we could go through and work out. So I can rewrite this in a particular form. So in the form that matches what we're used to seeing, what we want to see. So x cubed plus y cubed minus z to the 4 is equal to 4. All right. So at this point in time, we expect you to recognize that I can do this trick if I rewrite the form. All right. Differential equation, rewrite it to match one of the forms we know how to do. Bear in mind that with first order differential equations, I've got my separable, I've got my linear, or it could be just a it could be sort of simpler than that. I've told you the derivative of function with respect to x is a function of x, and so I can integrate both sides. Technically, that would be separable, but we're going to ignore that detail. So we expect a little bit of rewriting. And so I don't know. We could no. So the reason this equation is interesting is it's unknown whether there is integer solutions for x, y, and z. All right. I remember why I know this now. Sure. So I'm not going to be able to find a nice point to work with. Oh, actually, well. No. You can actually, like, even just trying to think of one now, you're kind of going, I can do this. Nah, I think I'm gonna let that. Oh no. Let's do my normal. If we did cube root of 2, cube root of 2, 0, that would satisfy that point. All right. So we know there are no integer solutions, but we can go, hey, there is a non-integer solution. So some surface at a particular point. All right, so we're going to find my normal vector, which is going to be equal to the grad of my function. Let's call this g, grad of g, which is equal to partial with respect to x. So we're differentiating with respect to x, holding all the other variables constant. Differentiate with respect to y, holding all the other variables constant. Differentiate with respect to z, holding all the other variables constant. Sweet. That's exciting. All right. And so my normal at my point three times cube root of, I'm going to say 4. 3 times cube root of 4, 0. Okay. Now, you get told that you can create the tangent plane by doing normal dot with x as a vector minus x naught, where this would be your x naught. All right. So this is true. This is definitely true. All right. And I'm going to go, but that would be equal to 0. But I don't like that. I don't. I've never liked that particular form very much. If I do normal dot with x, y, z is equal to normal dot with x naught, y naught, z naught, your point. All right. This is identical. All right. All I've done is I've expanded the dot product over this and put the bit over the other side. However, what it's going to do is it's going to put these bits in, it's going to put it into X, Y, things involving X, Y, Z over here, number over here, straight away. And so I like it better. Literally, it won't make any difference. And you are allowed to simplify your form. All right. There is nothing stopping you choosing the form you're going to use to make the working you do at the next step simpler. It's one of those secrets that we don't tell you a lot about because, I don't know, they like to be secretive about stuff. They're kind of, actually, the real answer is we don't tell you about it because we expect you're going to figure it out for yourself. All right? It's a thing. So we're going to get 3 cube root of 4 times x plus 3 cube root of 4 cube root of 4 times y. There is no z is equal to. And the beautiful part about this is that I've got cube root of, so what this is like, 4 times cube root of 2 plus 3 times cube root of 4 times cube root of 2 plus 0. This number, this is going to be 3 times 2 plus 3 times 2 is equal to 6 plus 6 is 12. Slick. All right, we should put that on the screen so you can see what I'm doing. Woohoo, we got ourselves a plane. All right. So let's pause momentarily to do this. Yep, beautiful. Get rid of that. Don't need to see it. Okay. Now, that's one of the things we can do with this. All right. We can, I wanted to go back to, so next, and so under the heading of the sort of things I'll ask with this, calculating partial derivatives, etc., or we're going to find a gradient vector somewhere. We're going to use it in some way. All right. So, what I was looking at here, no, no, don't want to do that. That one, no, that one. Okay, so in this case, one of the questions we might go is which direction is this function increasing most rapidly? All right. And so, and we know the answer to that, don't we? All right. So, all right. In the direction of grad vector. All right. They love this particular thing, all right, because it is very, very useful. All right. So go back to one of the famous exams of years past. They have got the temperature on a hot plate. All right. And you are an ant on the hot plate. Which direction do you want to go in? Well, so it's a hot plate. Think about that for a second. If you're an ant on the hot plate, you don't want to go where it's hotter, do you? So I think they did say in the direction in which it cools most rapidly. And so the beautiful thing about this, so with the grad vector, it's like balancing a coin on the tip of a pencil, right? There is the direction of maximum increase. The direction of maximum increase is a decrease is the opposite direction. All right. There is that property in your notes. I forget exactly what it was. There is a thing. There's a property that literally says that the direction of the maximum decrease is the negative of the grad. All right. So all right. So these things work nicely. And amusingly enough, halfway between the two is horizontal. All right. If you think about it, that's the maximum, that's the minimum. That way is going to be, so you've got your sort of maximum increase in that one direction, maximum decrease in that direction. Perpendicular to that is going to be sort of where your null lines are, where your function value remains constant. All right. Did you use the phrase null lines earlier when we were doing topological maps? Equal to potential serves? No. Okay. Yep. That's fair. I feel like that might be doing a thing where we don't do that. Okay. Sure. You will. It'll be fine. You'll get there. Okay. So there is a little bit of understand that, like, when I've calculated a grade vector, one of the things in the back of my head is going to be, how are they asking me to tell them this piece of information? All right. So are they talking about calculating a plane from this piece of information, or are they going to ask me about maximum increase?
there is the maximum value. Maximum value for the directional derivative is the length of the grade vector. Yes, that's what you were going to say. I hear you thinking that. It's fine. All right. So we're gonna look at that for just a fraction of a second. All right. Directional derivative. Direction in the direction of u of some function f is equal to the grad vector of f dot with a unit vector in the direction we're interested in. Okay. Now, we all know that this is going to be like the length of our directional derivative is going to be the length of the grad vector times by the length of a unit vector times cosine of the angle between the two. Okay, we've all done this 100 times. Well, maybe not 100. If you've done it 100 times, you're probably going to remember it for the exam. Anyone want to tell me what the length of a unit vector is? 1, right. Actually, a trick question. I've seen that in like a year 12 exam and I'm like, really? All right. Really? Length of the grade vector times 1 times cosine of the angle between it. I can use this, all right? If I know the angle between the direction I'm interested in and the gradient vector, I could work that out. More importantly, I'm going to use the dot product to work out the angle between them, generally speaking. But if I'm asked for the maximum, this is where I go, this is how I go, this thing here is telling me, this is the piece of information that allows me to go, if there is 0 angle between the gradient vector and the unit and the direction vector that we're interested in, the direction we're interested in, this number is going to be 1. It is just going to be the length of the grade vector. It is how I know if I go perpendicular to the direction of the grade vector, I'm going to have the value is going to, the function value is not going to change. All right. It is how I know that if I go in the completely the opposite direction, where my theta is 180 degrees or pi, that this number now becomes -1, and it is the minimum value for the length of the gradient vector. So I can know these things just by exploiting this piece of information. All right. We're allowed to go, hey, it is a dot product. Therefore, I can use the information I know about dot products. All right. Wasn't supposed to be, we didn't go, hey, it would be really useful if this worked out this way. We did this and we go, oh, hey, check it. That is a dot product. I can now say this. Okay. So we are allowed to do these things. Okay, cool. Okay. We're good so far. Any questions that crop up? So, yeah, so if you look at, I think, was it in the sample exam or was it one of the assignments? So if you think about it, when you're trying to work out what you might get asked, the assignments are a good indication of the things that they might use to ask. All right. So there was that question of you know, what is the gradient vector at this point? What is the directional derivative at that point in this direction? And the key with that is if I tell you what they will, I don't think I've ever seen them give you a unit vector when they've said, what is the gradient, what is the directional derivative in this direction? So there is always that step of normalizing. All right. When we're trying to find a directional derivative, we always normalize the direction we're doing the directional derivative in. So, and it's really important to be clear about what is the point we're doing the directional derivative at and the direction that we are going in, because they're both vectors. But one is a direction in that space and one is the point in that space that we're finding, where that one is the point we're at, one is the direction we're looking in. All right, can be, and this is what makes mathematics difficult for in some respects, in that we have to be really careful about which thing we're talking about. So getting used to, so people, like a common problem is people come up and go, oh, what is the null space? What is the null, what is the basis for this matrix? And a matrix doesn't have a basis, right? Matrix is a matrix. A space has a basis. Which space are you then talking about? So if I go, the null space of this matrix has this as a basis. I've said what part of what property of that matrix has a space and hence has a basis. All right. This is that same thing. A directional derivative, I need a point to calculate my directional derivative at, and I need a direction to be going in. All right. So key things, directions. So one exam, x-axis, right? They literally said in the direction of the x-axis. These things. And so y-axis is a similar sort of thing. Depending on your situation, right? So directional derivatives do apply in a two-dimensional sense, all right? If I go back to, let's, off the page again, aren't I? I'm a genius. If I go back to, I'm going to do this. So, so f of xy is equal to x squared y plus 4x squared plus 8y squared. Okay, sure. So this is from your sample exam. I'm going to go back to the camera for a second, well, to do the working. All right. So if I'm doing this, if I'm doing my grad vector for this one, so fx 2xy plus 8x, my f of y is going to be x squared plus 16y. Okay. So grad of f at, I don't know, 1, 2 is going to be equal to the vector. So 2 times 1 times 2 plus 8 times 1, comma, 1 squared plus 16 times 2. 4 plus 8 is going to be 12, and 32 plus 1 is going to be 33. And so this equation defines a surface in 3 dimensions, all right? Because we're effectively got z is equal to f of xy, all right? But because we're on a surface, we're only talking about a 2-dimensional direction for the direction of maximum increase. And so I would say, so if I do, so I don't know. Let's do this one, northeast. Okay. So a way to do this is to describe the direction as a compass direction. All right. And so what I'm going to do, northeast is that way, where that angle is 45 degrees. And so I can use the unit vector as cos of theta, sine of theta. Okay. And so I can go my direction vector, my unit vector in that direction. This is good because this is always going to be a unit vector. Okay. Cos of pi and 4 is going to be 1 on root 2, and sine of pi and 4 is 1 on root 2. Okay, so then I can go So it's going to be my gradient vector, 12, 33, dot width, 1 on root 2, 1 on root 2. One of the great joys of handwriting stuff and not having it computer marked is you can write this as 1 on root 2, 12 plus 33, which is equal to 1 on root 2 times 45. Okay, you can do that. You can take that horrible 1 on root 2 thing and put it outside. And in fact, at every opportunity, if I'm doing calculations by hand, I will do that. All right, I will try and put my constant out the front if I can. All right, and more importantly, because it's a dot product, if I have a constant on this one and a constant on this one, I can put them both out the front and multiply them together, which is really, really useful for doing things like the Gram-Schmidt process. Okay, so it's really useful to be doing those little things to make the next step of the calculation easier. Okay, okay, this part of the reason why I picked on this question, all right, is I thought it might be an interesting one to talk about finding and classifying critical points, because I'm not sure if we do a lot of talking about finding and classifying critical points. So what I'm going to do is I'm actually going to copy this information across. So okay, so the question this came from was find and classify all the critical points. All right. And so all right, so I'll need both first order partial derivatives equal to 0. Some places you'll hear it referred to as the first order condition, because first order is equal to 0. Everybody happy about this? This kind of sucks. I don't know if you've noticed this, but if I go 2x y plus 8x is equal to 0 and x squared plus 16y is equal to 0. That is not a lot of fun. All right, what I am going to do is I'm going to write this as 2x, and then I'm going to have y plus 4 is equal to 0. There is no clever thing I can do for this. All right, but this allows me to say this must be equal to 0. So if x equals 0 implies x is equal to 0 or y is equal to 4 minus 4 minus 4. Okay, so by noticing a factorization, all right, and factorization is your friend. In fact, factorization is like your best friend, right? We won't go into my favorite stories about this, but anytime you can factorize, you should factorize. Like anytime you can hang out with your best friend, you should be hanging out with your best friend, right? So it's a thing. It's like axiomatic, people. So anytime you can factorize, you should factorize. So what we're going to do, all right, x equals 0. All right, that means if y is equal becomes 12, 16y, which is equal to 0, implies y is equal to 0. So I have a critical point, 0 and 0. And that is the only critical point that occurs when x is equal to 0. Okay? Let's try y is equal to minus 4. This next to it, so my fy becomes x squared plus 16 times minus 4 equal to 0. You might notice that I get a bit fussy about putting brackets around negative numbers when I'm multiplying. All right. Really, really good habit. All right. Will save you a lot of missing minus signs or misinterpreting minus signs as a negation, as a subtraction, as opposed to a negative multiplying by a negative number. I have people tell me all sorts of things like it takes too long. It takes too long to draw brackets. Think about that for a second. How long have you spent searching for minus signs that you've lost? How long does it take to draw brackets? Don't need to make my point. X squared is equal to 64, x is equal to plus or minus 8. And so you can see with this one, I'm getting 2 critical points. I'm going to get 8 and minus 4, and minus 8 and minus 4. Okay, whoops, there we go. So technically for each of these, I need to calculate the Hessian. All right, need to do my partial derivatives. All right, so f x is going to be equal to, it's going to be like 2y plus 8. F x y, differentiate with respect to y, is going to be 2x. Differentiate that with respect to x, yeah, that's going to be the same thing. One of the things I always do, right? So what I've been doing, I've been working from the ones I've got at the top here. If I differentiate this with respect to y, that goes to 0. The x disappears, I get my 2x. If I differentiate this with respect to x, that disappears, I'm going to get 2x. I actually check, all right? Because that can be a way of going, oh, I've made a mistake earlier, all right? So if you have that inbuilt, I'm just going to check these things, all right? For simple derivative, and this is relatively simple derivative, then I can actually work out what each of these things is, all right? So I should be able to calculate my Hessian at the point 0, 0, which will be, so f of x is going to get me an 8. This is going to be a 0, this is going to be a 0, and this is going to be a 16, which is equal to, I don't know, 2 times 64 is 128. This is positive. So local, I think it's the local minima, isn't it? Is that right? Yes. Sweet. Let's do Hessian at 8 and minus 4. So when I put in 8 and minus 4 here, that's going to get me a 0 here. This is going to get me a 16. This is going to get me a 16. And this is a 16. This is equal to minus 256. And so I've got a saddle point. And annoyingly, I need more page. All right, sure. Let's go. All right. And so the last point, my Hessian at the point, what was my last point? Minus 8, minus 4 is going to be equal to, so this thing is going to get me a 0 here again. But this time it's going to be minus 16, and this is going to be a 16, which conveniently is still minus 256, and so another saddle point. Okay. Possibly I should go back a step. So the theory when we have a local maxima or a local minima says my Hessian is positive. I have either a local maxima or a local minima. I then look at, and I can use either fxx or fxy, fyy, sorry, because they pretty much have to have the same sign. All right. Yes.
I get 0 in the first one.
Here.
Next one down.
Oh, this one.
Yeah.
So because fxx is this, and we're evaluating when y is equal to minus 4, 2 times minus 4. Yep, good. No, it's kind of counterintuitive. You kind of go, it became 0 because of the value in the y coordinate, but it's a derivative with respect to x and x. It's just following, this says this is what I'm going to do, all right? can sometimes fight against your intuition, but it's what we're supposed to, it's what it is. I'm going to just put in the numbers. I'm going to try and sort of, I'm looking at this thing. This is what the equation is. I'm supposed to put in these numbers. I forget where it came from. Like I say, I've had arguments with people about a very similar sort of thing. And it is, you have a feeling that it should depend on the x because it's a derivative with respect to x, but the only variable in there is y, and so it depends on the y. All right. Technically, it is dependent on the x as well, but there is no x's. So when I've come to this, if I want to, I can go, hey, this is positive. I have either a maximum or a minimum. I now look at one of these, and you can choose either one. All right. The notes will say fxx because we want to be clear and give you a definite thing to look at. All right. But in proof, you can choose either one of them because for this, you think about it, these two numbers have to be the same. All right. The numbers on the off diagonal have to be the same. All right. For the Hessian to be positive, these two numbers have to have the same sign. All right. So it doesn't matter which one of these we choose. All right. And knowing that it doesn't matter can sort of relieve you of that stress of which one is it supposed to be. Okay. That is the reason for making this point. Okay. That is the only reason for making this point, really. So knowing little tricks like that can make your life easier. Yeah. Okay. Sweet. At this point in time, I'm going to pause and go, so, been an hour. Anyone got questions? No, keep making stuff up. It's fine. We're loving it. You look like you're thinking about something, Costa. Oh, symmetric matrices. Love symmetric matrices. So we love symmetric matrices because I wonder if we've got, I've got the notes loaded. Algebra. Linear transformations, diagonalisation, symmetric matrices. Sweet. Okay. I really need to zoom in on this so I can see what's going on. Symmetric matrices, eigenvalues.
Right, the ones that they asked,
Yep. So so when we give lecture notes, right, what we have to do is we have to build up to why these things are true. So you see that this first theorem, I need to change it so that the people on the Zoom can see. Question. It's a gradient orthogonal to the tangent line to the real. It would, so actually, should point out, yes. With going back to the thing about the gradient, this question here, the gradient. So because of that coin at the point thing, the gradient vector is pointing in the maximum direction, so it is orthogonal to the it is tangential to the level curve. Thought I said that, but just in case that point wasn't made, where was I going? I was going to go to where's the PDF? Okay, that one. So there are things like this result here, which are what we're going to use to base this on. All right. We actually need the eigenvalues to be real numbers to orthogonally diagonalize. All right. And we're saying orthogonally diagonalize because we're going to build up to saying, where is it? So this is the next bit that goes with this. All right. Let lambda be an eigenvalue of a symmetric matrix with multiplicity m. Then the corresponding eigenspace has dimension m. All right. So that's like, so what we're doing is, oh, it's real. We're going to use the fact that it's real so that we can go, hey, this thing must have a real eigenspace. All right. If it was a complex number, we'd have a complex eigenspace, not helping us diagonalize. Right. So what we're doing is we're going, oh, every eigenspace for symmetric matrices is maximum, is the largest possible dimension it could be. And so then we bring, hopefully the next thing they say is, if a real symmetric matrix, so if A is a real symmetric matrix, then the eigenvectors corresponding to the eigenvalues are orthogonal. Okay. So A real. I didn't do it. I didn't actually bring my notes. When I prepared for this seminar, right, what I did is I read these notes and I made notes. All right. So I've got, I think it's about, for 1B, I think it's about 10 pages of notes. Okay. It took me like 3 or 4 hours. It's actually kind of hard for me. Like, I would expect you to take longer because I will look at a lot of this and I will gloss right over it. But that process of making the notes on the notes is actually a really, really useful thing for you to do so that you know what we've said. And so what I did is I said, when I read that thing about, you know, the eigenvalues of a real symmetric matrix are real, I've gone, yes, I know that. I don't need to write that down. But what I have come down, when I have come down to this theorem, I've gone, this is the thing I need to know. Okay. This is one of the things that is useful to know. So that because what we're going to do is we're going to get you to create a matrix which will orthogonally diagonalize. And this is going to save you some work. Isn't this right, Costa? Right. So this is one of those things that can, by knowing this result, right, when I come to do this, I've got an eigenspace of dimension 2, eigenspace of dimension 1. I don't need to worry about this when I come to orthogonalizing my eigenvectors, right? That one's not involved in that. I only need to create an orthonormal basis for this eigenspace. All right. So I can focus on just doing that one. I don't need to worry about this other one. All right. Because I know the two distinct eigenspaces are orthogonal. If I have distinct eigenvectors, all right, if my 3x3 matrix, symmetric matrix has three distinct eigenvalues, each one of those eigenspaces will be perpendicular. And if I want, I can use the information to check my calculations. So knowing a way to check your calculation is a really useful way to do this. All right. So it's really important to go through and what are these things that I'm needing? What information do I have? Can I use that information to simplify what's going on? A real symmetric matrix. So all right, you'll find my notes literally said something like that. All right. Oh, poo. That one. That one. All right, they literally. All right. So making the notes is a really useful thing because it can help you. All right. Depending on where you are in this journey for preparing for this exam. And I'm going to go, most of you are probably doing quite well because I recognize practically every face in this room. You can actually then go, you can actually ask yourself, is there something I know that's going to make answering this question easier? All right. Like I say, you guys have probably heard me say, my friends didn't want to copy my assignments because I, quote, didn't write enough. All right. But I wrote everything that needed to be written. But by knowing that I could just say, I know these eigenspaces must be orthogonal, I don't need to check it. I don't need to prove that thing. I know it's true. And so I can work from that piece of information. All right. And so that simplifies calculating of the vectors I need to produce my matrix, which will orthogonalize. All right. Doesn't need to be set. Okay, so I can shortcut some of these processes to get down to these things. So, and this is, I think, what you were talking about, isn't it, Costa? That knowing some of these things. I'm going to switch back to the lecture notes just to sort of see what we've got. So then we define let N be, let a matrix A be called orthogonally diagonalizable if there exists a matrix P such that, so notice they're saying specifying orthogonal matrix. So that is what we mean by an orthogonal matrix. Okay, and so one of the beautiful parts about I've switched now. Wrong one. That one. All right. So we've got that the inverse for an orthogonal matrix, the inverse is equal to the transpose. We love this. Yes. All right. You guys are great. I can tell by that quietly laughing to yourself that I've stuffed up again. It's fine. So there is one of the problems with 1B is we taught you a lot of stuff in 1A. We're expecting you to remember that stuff. So you know how I said it's really useful to make the notes? If you made the notes, you could be looking at them. All right? Because that will remind you of some of those things that you thought were important about 1A. All right? And so if you make the 1B notes, right, when you're doing, say, multivariable calculus next semester, multivariable and complex calculus, you've got the notes that you can look at. All right? So you can do these things. And so the other thing to say is eigenvectors everywhere, man. All right. I did number theory, right? I'm like, oh, I could write this as a matrix. Oh, hang on. The thing that makes my life easy for this whole process is I can express everything in terms of the eigenvectors of that matrix. My friend doing what is it? Time varying switching systems. Right, complicated biomedical mathematical computation thing. So he's like, oh, if you write it in the thing, I'm like, I'm gonna just work out what the eigenvectors will be. And he's like, oh, that's gonna be the thing I need. And I'm like, yes. Because the answer to every problem is the eigenvectors. You ask David, I forget where they cropped up in his work, eigenvectors, all right? So if you can write it as a matrix, the first thing you should be doing is, how are the eigenvectors helping me? Okay, so may not be immediately apparent. And you may not get to do research mathematics. Don't know. Everywhere. So this is why we care about this stuff, all right? We care a lot. So we've got spectral theorem. If A is an n by n matrix, is orthogonally diagonal, blah, blah, blah. So A symmetric. If and only if. Fancy shorthand for if and only if. Asymmetric is, thank you. People. A is orthogonally diagonalizable. No. So this is where if and only if A is symmetric. It has to be real symmetric. I've got it. Yeah, okay, sure. All right. No. Actually, we should do A is symmetric if and only if orthogonally diagonalizable. That one. That's what we should say. Sweet. So we've got orthogonally diagonal. And so there exists B such that what is it? P transpose A, P is equal to D. All right, and you know D is equal to sort of lambda 1, lambda 2, lambda n. There's a whole lot of zeros around here. All right. So, do we need to really, so one of the great joys in life is when you go, so my A to my power 5 is going to be, A is equal to A is equal to P, D, P, P transpose. All right. And so 8 to the power 5 is going to be P, D, P transpose. You've seen this done, right? These bits here are the identity. Identity. Come on, people. Try that again. I know. Really, I do. P, D to the power 5, P transpose. But D to the power 5, we know is going to be like lambda 1 to the power 5, lambda 2 to the power 5, dot, 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 lambda n to the power 5. There's a whole lot of zeros around here. Okay, so they actually do this, and this is actually how they calculate fractional powers of matrices. All right. In theory, we can't find the square root of a matrix, right? This is what we do if we're finding the square root of a matrix. Okay, so it comes up. I actually don't know where I know it comes up in physics and some engineering areas, but I don't actually know what they are. Yes. Yeah, sure. All right, we'll pause for a second. Oh, covered enough of what you were thinking? Yeah, cool. Okay, let's go practice exam. Practice exam was fourth question. No, that was total. Question 2. Question 3. Question 4. Oh, so, all right, let's do this. I'm going to write this down. So because it doesn't, if I'm really clever. Okay, use the characteristic equation to find the eigenvalues and eigenspaces. Woohoo. All right, you guys are not in. Okay, let's do this. That one. Okay, people sometimes I have actually got asked whether it should be determinant A minus lambda I equals 0 or lambda I minus A equal to 0. The answer is it makes no difference. Okay. The reason we do this one as opposed to this one is it means the leading coefficient will always be positive. Okay. So that is in fact the only reason that I have ever heard for why we do that. All right. You can use either. But we want this thing. It's just nicer. If the dimension of the matrix is even, then it doesn't matter. But if it's odd, you're going to have a leading coefficient with a negative value. And since we're only interested in the zeros of the determinant, so the determinant of lambda minus 1, 2, 2, lambda minus 1 is equal to lambda minus 1 squared minus 4 is equal to 0. lambda squared minus 2 lambda plus 1 minus 4. And so lambda minus 3, lambda plus 1. All right. All right, so lambda is equal to 3 or minus 1. All right. Okay. We are actually trying to find these things here, right? We want the x such that this is true, but we want non-zero x, all right? So that's why we did lambda x, ax minus lambda x is equal to 0. And then that's where so we're actually solving that system, all right? So we are finding the null space of that matrix, which is that matrix, all right? So I want to put that in context. So firstly, this is the defining characteristic of eigenvalues and eigenvectors. If you are asked to show something with eigenvectors and eigenvalues and you don't know what to do, go back here, all right? This will make your life, this will probably be the answer or the first step on the answer, okay? So have had spectacular success proving things I've never heard of before just by writing this out as the first step and then going, oh, why don't we write that? Okay. So we are going to go lambda is equal to 3. And so if lambda is equal to 3, that's going to be 2 and 2 and 2 and 2. We're doing the null space. If you do not get a free variable, you made a mistake. Okay? So this is going to be 1 minus 1 as your eigenvector. Going to put a little tree to indicate he's the eigenvector for lambda is equal to 3. And so lambda is equal to minus 1. This is minus 2, 2, 2, minus 2, 0, 0, 1, minus 1, 0, 1. We have a real symmetric matrix. These things should be orthogonal. All right. Yes. All right. So it never hurts to do this if you are if you're aware of it. All right. I've calculated them. You notice we don't get you to do when you do the practice exam or whatever, there wasn't a lot of finding eigenvectors. All right. There may have been finding an eigenvector, and then we've gone, here's the other eigenvector, because we don't want you to spend a lot of time finding eigenvectors. We want you to demonstrate you know how to find eigenvectors. We want to tell you that information in some other way to make your life easier. What was I doing with this? Now that I have my eigenvectors, what were we? No. So the question was just asking for and corresponding eigenspaces. Woohoo! So technically, this is so. All right. All right. I'm going to express the space as defined by this basis. All right. Could have equally well done yeah. I swear. What you really want is 2 screens, really. That didn't go. Let's do this thing. That one. I did my. Let's try that. And let's go. Right. Okay. Sure. Could write it as a set. Could express it as defined by this basis. All right. Yeah, yep. Yep. Unfortunately, we have to go here so I can see this. What did B say? Find the orthogonal matrix and verify that P is orthogonal. And then calculate. All right, sure. Okay. So we want to find the P. Come on. Why not doing it? Sweet, that one. That'll do. Good. Okay. That was 7. Okay. So my P has to be enough. This one? Oh, good question. Does it matter? Yeah. All right. This is equivalent to -1, 1. All right. So because it's a basis, the direction is the thing that matters. So the length doesn't matter. And so that means multiplying by a scalar, specifically -1, doesn't change whether it's a basis. Okay. So this is one of those things mathematicians do. You know, like I was talking about putting my coefficients in alphabetical order where I can. All right, where I'm allowed to. If I have a choice of starting a vector with the -1 or not, I don't. All right. So it's kind of a little bit arbitrary because sometimes if I start it without the -1, but every other thing has got a negative in it, I'll go, no, I'm gonna reduce the number of minus. So there's like a reduction of number of minus signs, which is sort of a little bit dependent on sort of making the first one not negative. All right, we don't like, yeah. So it's a little bit arbitrary. Yes. Yeah. Yep. Span of this is a basis for because we're defining the space in some way. Okay, where was I? Oh, so when we're coming to find an orthogonal matrix P, right? So with my eigenvector, they're going to go in as columns. I need them to be length 1. All right, so I need my vectors to be length 1. And so I'm going to go 1 on root 2 by 1, 1. Similarly, 1 minus 1, we're going to use 1 on root 2, 1 minus 1. And so your matrix P is equal to 1 on root 2, 1 on root 2. So that's that column. And this one, 1 on root 2, minus 1 on root 2. Okie dokie Joe. So the question actually said verify. Verify that this is an orthogonal matrix. I need to do P transpose times P to verify that's an orthogonal matrix. Conveniently, I've set this up so it's a symmetric matrix, which is, and I'm going to put my 1 on root 2 out front here because I really don't want to have to do that. Times by 1 on root 2 and then 1, 1, 1 minus 1. And so I'm going to get 1 on 2 out the front here. 1 times 1 plus 1 times 1 is going to be 2, and a 2, and a 2, and a 2. So notice with this last one here, 1 times 1 plus minus 1 times minus 1. So going to be positive. And so, hang on, whoops. Watch me. That number is a 0. That's like 1 minus 1, and that's a 1 minus 1. Yes, I know what I'm doing. Beautiful, good. Which is going to be half times, it's going to be 1, 0, 0, 1. So what we have shown is that P transpose times P is equal to I. All right. To verify, you need to show that it meets the definition. All right. To verify this function is a solution to this differential equation, I differentiate in, put and show that it does this thing. All right. You notice I didn't start this equation with equals I. All right. Because I want to show that it is equal to I, not state that it is equal to I. Okay. So you can do, I think, want to show Pt times P is equal to I, but you do not start with that. All right. You start with one side of it and show that you get to the other side by following some mathematically logical steps. All right. Really important. Yes. Yep. Yes. Yes, you could do that. You could show that they form an orthonormal basis for whatever. So if you're going to show that the dot product is 0, you also have to show that the length is 1. All right. So, you know, E1, E2, E3, E1 dot E2 is equal to 0, but E1 dot E1 is equal to 1. So you need to show both parts. This is effectively doing it in one hit. It is equivalent. All right. You should be aware that for a matrix multiplication, I can express it as a dot product between the row of the first matrix and the column of the second matrix. So I can do that. All right. That is a way to do this. And it can be really helpful if I know, for example, these things are eigenvectors in some respect. These are eigenvectors or whatever. So can make your life easier. And so we could go through and find the fourth power of A. I don't know that anyone really wants me to do that, do we? Nope, nobody cares. We know how to do that. We know what we are going to do. We're going to go A to the power 4 is equal to P D to the power 4 P transpose. Got that the right way around, I'm pretty sure. We should make sure, tell me if I've got these wrong when you got the notes. Yes.
It's a question, but do you have to normalize the vectors if it's just
Yes, yes, you do. All right. If you think about what would have happened if I didn't normalize, all right. Yeah. So so when I'm just diagonalizing as opposed to orthogonally diagonalizing, all right, that inverse, creating that inverse, so my matrix P has determinant P. The inverse of that matrix has determinant 1 on P, and so when I multiply them together, I get 1. All right, because I'm just using the transpose, so the determinant of the matrix P is equal to the determinant of its transpose. If that number is not 1, then I'm creating a multiple of what I'm looking for, right? So if that was 2, when I did this process, I would be sort of getting twice what I should. All right. Well, actually, probably 4 times, but anyway, I'm not going to go into it. So yeah, it's like when I'm doing my orthogonal projections. All right, I need to normalize it, otherwise I get a factor of the length of that vector, and so I don't get the correct projection. Yeah, actually, really good question, really. Anyone? Cool. Oh, that was this bit. Was it part A? What was part B? It was a question. Oh, okay. Like that. Part B. Oh, suppose this is not diagonalizable. Right. What people question? Can you please go through a bit of theory deriving orthogonal projections? Yeah, okay. Yep. We will talk about orthogonal projections in a bit. I need to. So this is the question people are asking. Suppose C is, so C, I'm going to make me some notes. C not. Not diagonalizable given, so lambda 1 is equal to -3, race is equal to 7, and determinant of C less than 0, negative. Okay, I love this. This is kind of funky. So we've got a matrix. We know it's 3 by 3, so we know we've got 3 eigenvalues. We know it's not diagonalizable. So we've got an eigenvalue of -3, we've got a trace of 7 and a determinant. So this is actually I love this question. This is like, honestly, whoever wrote this was on their game. All right. Because there's a really subtle thing in there. All right. So let's talk about it. That's right. Good. So trace. We love the trace. Trace is the sum of the eigenvalues. This is telling me that lambda 2 plus lambda 3 is equal to, wrong thing. Yep. Doing this. Yes. So you notice at the start, and if you looked at my exams back when I was an undergrad, you would have seen this thing, would have seen the same thing. Okay. All right. So 7 plus 3 is equal to 10. All right. Determinant is negative. So -3 determine -3 times lambda 2 times lambda 3 is less than 0. Therefore, lambda 2 times lambda 3 greater than 0. Okay. So if we tick off what we've done, we've used that, we've used that, and we've used that. We haven't used this. How are we going to use that? If we go back to what it meant to be diagonalizable, it meant, so I think that it may, yeah, you want to tell me? Yeah, I can't get a full 3 basis vectors. All right. Now we know the minimum dimension for an eigenspace is 1. So if I have 3 distinct eigenvalues, then I must get 3 eigenvectors, and this thing would be diagonalizable. So I can only have 2 distinct eigenvalues. All right. Now, interestingly enough, if lambda 2 and lambda 3 are both, or I could have 1 distinct eigenvalue. So what I'm going to do is I'm going to consider this and go, if lambda 2 and lambda 3 were both -3, this would not be true. All right. So can't be 3, so all right. They must be equal, because I must have an eigenvalue of dimension 2, multiplicity 2. All right. Can't have distinct ones because that would be diagonalizable. Can't have 3 because that doesn't meet the other criteria. Must be that I have an eigenvalue of dimension of multiplicity 1 and an eigenvalue of multiplicity 2. Because I know the matrix is not diagonalizable. All right. This is using that piece of information to imply that I have a repeated eigenvalue. I have an eigenvalue of multiplicity 2. It's a real, like, frighteningly clever thing. How? Yep, no, take some time to think about that. This is being recorded. The recording will be uploaded probably by the end of the day because David's really good at doing that. Interestingly enough, it goes to his cloud because he's the one who set up the meeting. Anyway, worry about it. So this means lambda, and so lambda 2 is equal to lambda 3. And so if I rewrite this, all right, that means this must always be true. Therefore, lambda 2 times lambda 3 greater than 0. Always true. But then I have 2 times lambda 2 is equal to 10. And so lambda 2 is equal to 5, which is equal to lambda 3. So what are all the eigenvalues? All right. -3, 5, and 5. All right. And so that's all I need to know. I don't have to worry about any more than this because I've used the information given to work out, to imply that I must have a repeated eigenvalue. All right. Like I say, when you think about what's involved there, really, really tricky, really difficult stuff. Okay. Are we good to go? Love and life? Yes. Okay. Projection. So I'm going to have a bit of a scan through the thing and go projection. We should create ourselves. Let's do this. Okay. Terrible plan, but I'm going to do it anyway. So if I take my vectors 1, 1, 1, and 1, 2, 2, and 1, 2, 3, I happen to know that they must be linearly independent. All right. This is trust me on this. So if we're going to do anything about orthogonal projection, if I go, hey, there is a space spanned by these vectors, do the orthogonal projection onto this space, all right, they will not get you to do this much in the exam, okay? Doing Gram-Schmidt process for 3 vectors is just too much, okay? However, my V1 is going to be 1 on root 3 by 1, 1, 1. The U2 dashed is going to be sort of 1, 2, 2 minus 1, 2, 2 dot with 1 on root 3 by 1, 1, 1 times by 1 on root 3, 1, 1, 1. So 1, 2, 2 dot product. So I'm going to go -1 on 3, putting those two together. This dot product is going to be 1 plus 2 plus 2. It's going to be like 5 times by 1, 1, 1. So it's going to be 1 minus 5 on 3, so -2 on 3. 2 minus 5, so it's 1 on 3, 1 on 3. Everybody's loving that. I am creating an orthonormal basis. I'm about to multiply by a constant to make this vector length 1. I am going to choose to multiply through by 3 before I do that. Because I'm going to multiply by a constant, I could maybe multiply by a constant first to make my life easier. All right. This is equivalent to -2, 1, 1. And so my V2, I'm going to write as 1 on square root of 6 by -2, 1, 1. Okay. Now, at this point in time, I'm going to go the next step, all right, because V3 would be U3 minus, and then U3 dot V1 times V1 plus U3 dot V2 times by V2. What I might do is I might do these bits separately. Okay? Yes, they're still on screen. Good. Rather than trying to do it in one big long calculation, I can do this bit and I can do this bit and then I can bring it all together. All right. And this is just being careful about what I'm doing. All right. My V1. So I'm actually going to be lazy and put, and see how I've had my 1/3 and my 1/3, my 1 on root 3 and 1 on root 3, and I put them together and it became 1/3. I'm just going to save myself some time. All right. And so I've got 1, 2, 3, dot with 1, 1, 1 times by 1, 1, 1, which is going to be, so 1 plus 2 plus 3 is going to be 6. So 6 on 3 times by 1, 1, 1, which is going to be 2, 2, 2. All right, loving it. U3 dot V2, V2. Again, I'm going to be lazy and put my 1 on 6 at the front. And then I'm going to do minus 2, 1, 1, dot with 1, 2, 3 times by 1, 2, 3. So 1 on 6 times by, so minus 2 plus 2 plus 3, going to be 3 times by 3. And then by 1, 2, 3. So that's going to be a half of 1, 2, 3. Yep, good. That checks. Okay, so now I'm going to do 1, 2, 3. No. 2. Except this number is going to change. That's going to be a 2. Watch me. I know, that's really annoying. What we're going to do, we're going to go, I'm going to write that out again for the recording. Sorry, guys. U3 dot V2, V2 is equal to 1 on 6 minus 2, 1, 1, and then 1, 2, 2. So that's dot product, 1, 2, 2. And so dot product, minus 2 plus 2, 2. So it's going to get me 2 on 6 by 1, 2, 2. And I'm going to leave it as 1 on 6 by that. Okay, so now I've got 1, 2, 3. Take away 2, 2, 2. Take away, that's a third of 1, 2, 2. Which is going to be equal to, I don't know, 1 take 2, take a third. 2 take 2, take 2/3. And 3 take 2, take 2/3. Which is going to be minus 4 on 3. Minus 2 on 3. And that is 1, so that's 1 on 3. Again, going to multiply through by 3. Minus 4, minus 2, 1. And yes, I went off the bottom of the screen, didn't I? Thank you. And so now my V3, 16 plus 4 plus 1, 1 on square root of 21, minus 4, minus 2, 1. All right. Depending on how you feel about that, you could have equally gone with all right, because I can multiply through by a scalar. All right, because direct basis vectors, the important part is the direction, not their length. Although we're creating an orthonormal basis, I need to preserve length 1. Changing the direction does not change the length. Okie dokie joke. All right, so we have our orthonormal basis. I don't know, yes. Which one? Oh, did I do it wrong again? Yes. Yes, yes, I did. Proof. All right, let's try that again. All right. Do you want to know why Gram-Schmidt process in the exam is hard? U3 dot V2 by V2 should be. So U3, 1, 2, 3, dot width, dot one. I should have had 1 on square root of 6 minus 2, 1, 1. Times 1 on square root of 6, 2 minus 2, 1, 1. All right, this time for sure. You could have told me sooner. Yeah, yeah. Okay. All right. Dancing music, people. So minus 2. So this is going to be 3. Oh, good. That makes my life work better. And then minus 2, 1, 1 is going to be, so that's going to be a half of minus 2, 1, 1. And so when I come to doing like B3 dashed, it should be 1, 2, 3, minus 2, 2, 2, minus a half of minus 2, 1, 1, which should be 1 minus 2 plus 1. Oh, that works better. Who doesn't love that? So it should be like 2 minus 2 minus a half, and 3 minus 2 minus a half. And so that should be equal to 0. Minus a half, a half. Sweet. And so we are going to 0 minus 1, 1. And so V3 is going to be 1 on root 2. All right. At this point in time, since I've stuffed it up like 3 times, we should check. We should so check. All right. So my V1 we said was, what did we say? We said that was 1 on square root of 3 by 1, 1, 1. My V2 we said was 1 on square root of 6 by 1, minus 2, 1, 1. And V3 we said was 1 on square root of 2 by 0, 1, minus 1, 1. Okay, so dot product. Quickly doing the dot product between these two. So minus 2 plus 1 plus 1, 0. Woohoo. These two, 0 minus 1 plus 1, 0. Woohoo. 0 minus 1 plus 1, 0 again. Woohoo. All right, beautiful. Yes. Yeah. So I'm creating an orthonormal basis. All right. So yes, you're going. So I hear what you're saying, right? I wanted to do this with not ordinary vectors, but I didn't want to add in a fourth component. So you're going, hey, these span R3. Couldn't I have done like 1, 0, 0, 0, 1, 0, 0, 0, 1? Yes, you could have. All right. Wanted to demonstrate the process of doing this for vectors which are not difficult, but not simple. So doing a row reduction, like creating the matrix and doing that row reduction creates a basis for the matrix, for the space spanned by those vectors. All right. But it does not create an orthonormal basis. All right. So there is nothing about the basis that will create, that will guarantee it's all that their vectors are mutually orthogonal. All right. Yeah. So I mean, like if they said create an orthonormal basis for this space, gave you 3 vectors in R4, say, then you could go through and simplify, work out, sort of do some, like enter them into rows of a matrix, do some row reduction to simplify the vectors you're working with, get a lot more zeros in those vectors, and then start that process. That will annoy the marker. Thinking about having people doing things like that, you can go, yes, that will create an you can do an orthonormal basis by changing the initial vector. But it won't necessarily, so like it's not, nothing about doing row reduction will actually create a simpler vector. Okay, it won't necessarily help. All right, the row reduction doesn't do anything to create an orthonormal basis. All right. If you, so this is that, so you can, if you have n vectors in Rn, then you like, if you were asked to find an orthonormal basis for it, a trick would be to go, they're all linearly independent, therefore the standard basis for Rn is an orthonormal basis for this space, because it is Rn. All right. All right. If it's a subspace of Rn, then no. Okay. It occurs to me that we're after 12. I'm happy to keep talking about stuff for the next half hour or so, or an hour, till the drop-in center opens, or we can stop here. This will go up online. Remember, there is revision seminars on just about everything. So if you go to the Miscellaneous Center website, resources, find 1B, there will be a whole lot of David's revision seminars where I don't make mistakes because David did it. Okay. So yeah. No worries. Good luck with the exams. But I will be talking to at least some of you in the not too distant future, right? Or have all the assignments for 1B been handed up? Is today the day the last one's due? Oh, oh, hey. I'm gonna stop sharing. Okay. Okay, thank you guys online. I'm going to stop the recording now. Come and talk to me, or hit the drop-in center Zoom at 1 o'clock when we open. Thank you.